Hey everyone, welcome to Coding Simplified, and today we'll see about the DFS traversal using adjacency list. Now DFS means depth first search. So DFS is one of the strategies to traversal the graph. Now let's take this example. So here we have graph where we have 7 indexes. So now let's assume this like this, that let's say there are 7 cities and we are representing each city which is index. So this is like first city, this is second city, third city, fourth city, fifth city, sixth and 7 cities, right? Now there is a person and who need to travel all the cities. So let's say there is a starting point. So like in our case, let's say if my starting point is this 0. So the person is starting from here and he need to travel all the cities. Now what will be the strategy to travel, like which city he will go first? So that depends on the strategy that we are following. So like either we can follow the BFS where we go in the breadth first search. So in our last video we basically covered the BFS traversal. So if you want to know about BFS, you can see our previous video. Now in this question we'll cover the depth first search. So depth first search, it says that first of all I will go in depth and then I will cover the other element. So what will happen in this case? Let's say if I'm starting from here, so either I can go to 1 or I can go to 2, like, so that is fine. I can go either 1 or 2. So now let's say after traversing this element, then I'm going to second element. Then what will happen, that after going from here to here, then after that it will not go into 1, because in BFS what happened, that it covers in the breadth. First it will cover 2, then it will cover 1, then it will cover 2, then it will cover 4, then it will cover 3. But now here, as soon as it covers this one, then it immediately go to its child. And because this is undirected graph, so 0 is also child, but 0 is visited, right? But 0 is visited, so in this case it will go to 4. So if you see here, from 0 to we reached at 2. Now from 2 we immediately go to its depth, and for 4 we immediately go to its depth from here or from here. So it can go to any child, but the point is that we are going in depth, right? And once it will cover this portion, then it will go to that portion. So this is the concept of depth first search. Depth first, that first of all it will go in the depth and then it will go to other elements, right? So this is about the DFS. Now here we are using the adjacency list. So point is that we can represent a graph in two ways. Either we can represent using adjacency matrix or we can represent using adjacency list. So if you see our graph playlist, in this first or second video we have explained using adjacency matrix, the DFS traversal using adjacency matrix. So today we'll see that how we can represent the graph using adjacency list and how we can do the DFS traversal when we have the adjacency list. So now if you see, this is undirected graph, right? So how do we represent this graph in adjacency list? So basically, first of all what we do, we basically take a data structure. So data structure, like in Java, we can take the list of list. So basically list of list means that we have a list where each index is also representing a list. So what it will do, it will basically have all the children which are associated with this particular index. Now if you see this case, this is 0 index. Now which are the children or which are the neighbors? I would not say children, I would say neighbors. Which are the neighbors of this city, of this index? So neighbors are 1 and 2. So that's what we have written, 1 and 2. Now what are the neighbors of this 1? So because this is an undirected graph, so from here I can go to this direction as well and this direction as well. So the neighbors of 1 is 0, 3. So if I say from this city where I can go to this city and this city. Similarly, if you see this city, this index from 2 I can go to 0 and I can go to 4. So I have written 0 and 4. From 3 I can go to 1 and 5. So I have written 1 and 5. From 4 I can go 2, 5 and 6. So I have written 2, 5th and 6th. From 5 I can go 3 and 4. So I have written 3 and 4. And from 6 I can go to only this index or this city. So I have written this one. So this is a way so that I can represent the graph. So what will happen, that through our code, whenever we'll initialize this graph, so at the same time I will create a list, and then at the starting I'll create an empty list. Now according to edges, because these are the edges, so whenever I'm adding any edges, so basically I'll point in both the direction, from 0 to 1 and from 1 to 1. So what will happen at this moment, let's say if I'm adding this edge, if I'm adding this 0 to 1 edge, so what I'll do, because I know that I need to add neighbors. I need to add neighbors from this list, and I need to add neighbors in this list. So first of all, I'll get this point, that get the list at this point and then add one into this list. So I'll add one to this list. Similarly, I will do the same thing, that get the list present at this index and then add 0 into this one, right? So this is how I will add a particular list. So when you will see the code, so I'll again explain you this one. So it means now we have seen that what is a DFS traversal and how we can represent the graph into this one. Now let's see that how we actually travel in the depth first search. So like, let's say this is my starting point, right? So in BFS we saw that BFS traversal can be implemented using the queue, and whenever we talk about the depth, then we always take the stack, right? Because if you are using recursion, or like we are using, if you want to go in depth, so we always use the stack. So what I will do, that I'll take one stack. So here this is one stack, and I'll take one boolean array which will have the size equals to the indexes. So this is 0, 1, 2, 3, 4, 5 and 6. So it means this will cover basically all the nodes that we have. Now at the starting, all values will be the default value, which is false. So what will happen, this is basically the array of visited. So through this we can maintain that how many elements we have visited, or like if we have visited a particular node, so there is no point to go it again and again, right? Because my point is to traverse the one city only once, that I will travel this city and then I will move forward. So that is why we need to maintain that which city I have visited, right? Because what can happen, let's say from 0 we started and I go to 2. Now because 0 is also a neighbor of 2, so when we'll see, so this will say okay, the 0 is also neighbor, so you need to go there. But if I have already visited, so there is no point to go again. So from here I will check that whether this element is visited or not, right? So let's start the first of all. So this is my stack. Now what will happen, that first of all I'll put the starting index into this stack. So starting index is 0. Now you can start from any point. It's upon you that from where you start. But let's say we are starting from this index. So now first of all I will put this starting index into stack, right? Now once I put this one, so now I will remove the stack from here, the value from here, and so this will give me 0, and I will put okay, this is the first city where I am doing the traversal. So it means currently I am at here, I am at this city. Now I will check that okay, I am here, but what are the neighbors of you? So how can I get neighbors? So you know that we have this list. So from here, from the index of this one, I can easily get which are the neighbors. So it will give me the neighbors as 1 and 2, right? So now what I will do, then whatever the neighbors it has, now for each neighbor do one thing. First of all, check that whether this element is visited or not. Now if this element is not visited, it means mark this value as a true and just put this value into stack. So like first of all, the first children is 1, so I check here, and like when we put the value 0 here, so I have already marked it as a true. Now what is the neighbor of this 0? The first neighbor is 1, so I'll check that whether one is visited. So from here I'll get this is false, so it means this is not visited. So I'll mark it as a true and I'll put in the stack. So now I'll put 1 as an stack. Now I'll cover the second children. Second children is 2. So check, second is visited. So from here, second is not visited. It will again mark it as a true and then put this value into stack, right? Now we have covered both the indexes. Now again pop the top element from the stack. So when it will pop this element 2. So it means after this one, now I am covering this city. So I am hit here now. So you see that from here I can go to any city. That is fine. I can go to here also and I can go to here also. So because this index was on the top of the stack, so now I am covering at this here. So now it means I am at here. So when I am here, so I will check that which are the neighbors of it. So the first neighbor is 0. So how can I check? I can check from here, because this is my index. So I'll get the list from here. So this will give me the list of that the neighbors of 2 and 0 and 4. Now I will check the first children. So check first with 0. So 0 is visited. So it will check from here. Yes, 0 is already visited. So it means we need not to put into stack. So that is done. Now we'll check the second children. Second children is 4. So I'll check that whether 4 is visited. So 4 is not visited. It means mark is a true and then put this value into stack, right? And now there is no more children. So now if you see, again I'll pop the element. So now the popped element is 4. So it means if you see here, the next pop element 4. So this is why, this is how we are doing depth. We started from 0, then we go to 2, then we are then I am here. So after visiting from here, then I went to here, and now I am here, right? So when I am here, so it means now you are at this index. So again I'll check that which are the neighbors of this one. So the neighbors are 2, 5th and 6th. So how will we get? It will go to 4th index from here, and it will go that give me all the neighbors list. So here it will give me 2, 5, 6. So here it will give me 2, 5 and 6, right? Now I will check one by one all the children. Now first of all check with this 2. 2 is visited? Yes. From here 2 is visited. Now I'll check the next children. 5 is visited. So 5 is not visited. So I'll mark as a true and I'll put this value into stack. Now 6. 6 is also not visited. So it means mark this value as true and then put this value into stack. Right? So it means now we are done. Now the top element is 6. So again we'll pop the element from here. So I pop the element here and now I am here. So it means after traversing this one, now I am here. Right? So you see that I'm going on all the depth. I started from here, then here, then here, then here. Now I am at 6. So I will check that give me all the neighbors which are related to 6. So the neighbors of 6 is 4 because I can get from here. So it will give me 4. Now the 4 is already visited from here. So it means I will not add into stack and that's it. Okay. So because there was only one children, so I will not go further. Now I will pop the again element. So now it will pop 5th. So the 5th is on the top of the list. So it means after here, from here, then I will go to here. So I am at here now, right? So again I will ask that give me all the neighbors of 5th. So 5th of the neighbors of 5th is 3 and 4. So how can I get from this list? So now it will give me 3 and 4. So I'll check again that whether 3 is visited. So no, 3 is not visited. So it means I'll mark as a true and then I'll add this value on the top of the stack, right? So 3 is done. Now 4 is already visited. So it means we'll not put into stack. So we are done. Now again what is the top element? Top element is 3. So I'll add this value here. So it means after 5th, now I'm going to here. Right? Because the point is it always covers the neighbors. So because 4 are already visited, so now it is going to 3. Okay. So now it will go to 3. So now it will again get that give me all the list which are there of 3. So it will give you 1 and 5. Now because 1 is already visited, so we won't add into list, and 5th is also visited, so we want into list. So we are done. Now what is the element left? So next element left is this 1 because 1 is here in the stack. So it will remove 1 and now it will add 1 here. So it means now from here, now I am at here. Okay. So now it will again ask that give me all the give me all the neighbors of 1. So the neighbors of 1 is 0 and 3. Now because 0 is also visited and 3 is also visited, so we want into stack, right? So now there is no element into stack, so it means we are done. So it means we'll cover this until stack is not empty. So if you see, this is the depth first search traversal for this particular graph or for this particular traversal. So what we started from this was the first element, then second, then third, then fourth city, then we covered this city, then we covered this city, then we covered this city, right? So this was the depth first search traversal. Now let me show the code as well so that you can get it better. So here is our code. The first thing that we are saying that how many nodes we have or how many cities or how many indexes we have. So here we are saying that total we have 7 nodes. So now I'm initializing this graph. So let's check here. So now in this what we are doing, that I know that I need to represent this graph as a adjacency list or like list. So first of all I'm creating the graph as a list of lists, right? Where it will have all the list and each list will represent the neighbors it has. So now that is why we are doing that. First of all I am initializing this graph. So now I am initializing with this new array list. Now I am passing the nodes, that how many nodes I have. So I need to create the boolean array. So that is why I am creating the boolean array of this size, right? Now after that we know that for each node, for each indexes, I need to create a new list, right? Because that list will contain the neighbors. So first of all, because this is the initialization, so I'm creating a blank list for each index. So that is why I'm doing that graph.add. It means add a new array list, new blank list at this particular index, right? So this is how we can create a adjacency list, or this is how we can represent the graph in adjacency list. So now I have done the initialization. Now after that, what it is doing? Now it is adding the edges. So let's go here in the edges. In the edges, what it's doing, it is saying that because this is a list, so it is saying give me the value which is present at this index at get a. So get a will give you the value. Now what is the value? Value is a list, because this is list of list, so it will give you the list. Now you are saying that in the list add this element, add this b element, right? Add this b element means add this b index, right? So now because this is undirected graph, so we are adding both in AB and also in BA also. If it was directed graph, so we would add only in the BA, right? So this is how we are adding the edges. And now after that, once we have done all the edges, after that we are covering this DFS, where I'm passing that what is my starting index. Now let's say if your starting index is something else, so you can give some other indexes. So let's go into DFS. So now this is starting index, this is start parameter. Now here I am initializing the stack where I will put where all the values will be the indexes, right? So this is the integer, that is why I am saying. Now first of all I am putting the start index or the start index into the stack, and I am marking this value as a true, right? Now I am going further and I'll operate this until stack is not empty. And now first of all I am popping out the first element, that what is the first element of this stack, right? So now it will give me an integer. Now I'll print this value, that it means now currently I am at this index, I am at this city. So now because this is the first city was a 0, so it will print the 0 first. Now I will get give me all the neighbors for this particular index. So how it will get? Because this graph represents the adjacency list, so what we are doing, we are saying that for this particular index, give me the list. So this will give me the list of all the indexes or all the neighbors for this particular node, right? Now for each node, so that is why we are iterating that for each integer means for each index for this particular child list. Now check that whether if this element is not visited, so that is why we are saying not visited. So if this neighbor is not visited, in this case you need to push this value into stack, right? So rather than this child, we can have the neighbor. So this is neighbor. So it will have the neighbor, and similarly for this child also write here neighbor. So this is basically neighbor list, not child. Right. So now it means for each neighbor it will check that whether this neighbor is already visited, and if this neighbor is not visited, it means push this neighbor into a stack and then mark this neighbor as a visited, right? So now one by one I'll do this until stack is not empty, like we explained, and then it will keep on printing the values in the depth first search manner, right? Now this was about the undirected graph. Now let's also see that how we can do this thing in directed graph. So let's see, we have this case here. So if you see from here that from this city I can go only to this city. Now from this city I cannot go to back because this is directed graph now, right? So this is the difference between undirected and directed. In undirected basically we can go in both the direction, but in directed graph we can only go in one direction. Where is the direction? So like if you see from here, from 0 I can go to 1 and 2, from 1 I can go to 3, from 3 I can go to 5, from 4 I can go to 5 and 6, and from 2 I can go only to 4. So the only difference in the adjacency list will be, now it will not be in the both the direction now. Now it will have the list only of one direction. It means from this 0 I can go only on to 1 and 2. So that's what we have written. From 1 I can go to only 3. So from 1 I can go only to 3. From 2 I can go to only 4. From 3 I can go to only 5. From 4 I can go to 5 and 6. So I have put this point into list, all the neighbors into list. So now I would say, now this is not neighbors, now it is where I am actually going, right? So it is now directed neighbors. Now from 5, if you see from this index I cannot go to anywhere, so it will be a blank list here. And from 6 also it will be a blank list, because from 6 I cannot go to anywhere, right? So now the only difference will be in the representation, otherwise all the things remain same. The traversal remain exactly same. So what will happen, that the same thing I will do here. First of all, I'll create a stack. So I'll put this 0 here, and then I'll create a boolean array here. So now it will be 0, 1, 2, 3, 4, 5, 6. So at the starting all the values are false. So now because I have put 0, so I'll mark it as a true. Now I'll remove the value from here. So it means I have covered this traverse. So it means currently now I'm at here. So what I will do, I'll get a list. So the list, it will give me 1 and 2. Now 1 is visited? No. So I'll mark as a true and I'll put this value into stack. Now it will check for 2, whether 2 is visited? No, 2 is not visited. So mark this value as true and put this value into stack. Now we are done with this one. So the next popped element is 2. It means now I am at this index. So now I have reached to here. Now it will again check that what are the where it can go from 2. So from 2 it can go to our 4th index only. So it will check whether 4 is visited. No. So mark here as a true and mark and put this value here. Now the top element is 4. So it means I am at 4th index now. So it means I am at here. So check with the 4th. From 4 I can go to 5th and 6th. So again it check whether 5th is visited. No. So mark it as a true and put here. Whether 6 is visited? No. So mark it as a true and put here in the stack, right? Now it will again pop the element. So now it is 6. So it means now I have reached here. So from 6 where I can go, this is blank list. I cannot go anywhere, right? So it means I will not operate anything in this. Now after it will again pop the element 5th. So it means now I have reached here. Now from 5th where I can go. So again it's a blank array list. So it means I cannot go anywhere. So I won't do anything. Now the next element is 1. So the next element is 1. It means it will check that from 1 where it can go to 3. So it will give me the 3. Now it will check whether 3 is visited. No. So if 3 is not visited, then mark this value as true and just put this value into stack. So we are done. So, okay, so when we removed 1, it means now I was at here. So it means I was at here. Now check again. So now what are the element left? The element left is 3 in the stack. Remove this one. So remove this one and then put here. It means now I am at here. Now where 3 can go? 3 can go to only 5 and 5 is already visited. So it means we won't do anything, right? And now there is no element left into stack. So if you see, I have covered all the elements. So this will be the iteration if we have this directed graph. So first it will traverse 0, then it will traverse 2nd, 4th, 6th, 5th, 1 and 3, right? So if you see that there is no major difference if you are covering undirected graph or directed graph, the only difference will be in the code. So what we'll do, and even there will be just a small difference, because the point is that when you are initializing the graph, so this will be the same as it is, because we need to create an empty list and all that thing. The only difference will be in the edges, that whenever we are adding any edge, so earlier we were adding in both the direction, but now it will add only in one direction. So that's the only difference will be happen in the directed graph. Otherwise all the things will remain same, right? So if someone asks you about the directed graph, you can just have only one item here, that graph.getAdd.addB. If it is the undirected graph, then you can add both the things, right? So that's about the directed graph. Now if you see the time complexity to solve this question, so basically what we are doing, we are covering each vertexes, each node and each edges, right? If there are e edges, so if there are v vertexes and e edges, so we are covering all the edges and all the vertexes. It means my time complexity will be this one. Now if you talk about the space complexity, so what extra parameters that we are using here? We are using one queue and we are using one adjacency list to represent the graph. So first of all I am taking this queue. So how many elements are there in the queue? The elements are here equal to the nodes. So it means it will be big of v. Now for this list, because list is, we are taking list, so the point is that these are the nodes, that is fine, but here also how many elements will be there? So the elements will be there equals to the number of edges we have. So it will be again v plus e, right? So it means the space complexity will also be equal to this one, right? So that's it guys about this video. and if you have any doubts about it, then please write in the comment section. I will try to explain that, and I will also put the source code into description section, so if you want, then you can also get it from there. So that's it, and if you have liked the video, then please like it and subscribe the channel for more such videos. Thank you.